Hi, today is module 2, lecture 3. We're going to be talking about hypothesis testing for categorical data. So just, to assuage anybody's worries, all you need to know for continuous data is how to use the function t.test and how to use the function wilcox.test and to interpret it. That's it. That's all you need to know how to use. So it's going to be the same thing here. I may show you some formulas or whatever, but in the end, all you're going to need to know about is two other functions, which is chi-squared.test and Fisher.test. Those are the only two functions that you actually need to know about in this. Okay. So do not be afraid by these, but I need to give you this kind of information because it's good to have that background. And for those of you that are interested in pursuing more kind of statistical training, it's important to kind of know where these things come from. All right, so where did I have my Moodle here? So if I go to Moodle, lecture 3 resources, this is the lecture code again. So you can see this here. Again, what I recommend you doing is just kind of walking through all of these. And here's the lecture slides. So let's open up the lecture and get started. Okay. Hypothesis testing and confidence intervals for categorical data. So categorical data would be something like binary, like a coin flip, right? One coin flip is binary. That's category. You can either get a heads or tails. How many heads you get out of 10 flips, that's binomial, but it's also a category, right? It's a 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, 10 heads, one of those. A Likert scale, strongly disagree, no opinion, agree, strongly agree. That is also categorical. Patient races, patient medical history, did they have hypertension, whatever, those are all categorical data. So this is going to be hypotheses for those kind of things. So again, I have these examples here, binary data, 0 or 1, Likert scale data, 1, 2, 3, 4, or 5, weather patterns, is XI rainy or sunny or cloudy, cancer stages, 1, 2, 3, 4, these are all categorical data. Okay, first let's start with binary. So binary is going to be 1 or 0. So consider a binary random variable 1 or 0. So in the example, maybe you want to know, did someone die? Okay, what's the likelihood that somebody dies given that they have, I don't know, advanced cancer, for example? Maybe we want to test that. So pi, which would be the probability at xi equals 1. In this example, it would be the true probability that someone dies given that they have advanced cancer. And it could be a different type here. Now, what we can do is we can test a bunch of different hypotheses, just like with continuous data. So we can test whether pi is equal to pi 0. Pi 0, for example, could be 10%. Okay, is the risk of death if you have advanced cancer 10% versus something else? That's a two-sided test. You could check, is it less than? You could check for in COVID, for example, is your risk of death less than 10% or is it higher? Less than 5% or is it higher? Whatever that number is, you can test those numbers based on data that you actually collect. How do you collect it? In that case, with COVID, you go out and you collect information from patients, they get hospitalized, and you count how many people died. Did each person die? Yes or no? The proportion of people that died is sort of inferring on this probability of death. Same thing with cancer. If I wanted to test whether a coin is fair, I might test that the probability of getting a heads is 0.5. Flip a bunch of coins, count the proportion of heads. So if the null hypothesis is true, pi equals pi 0, then this test statistic below has a normal distribution with mean 0 and variance 1. So it's going to be x bar. In this case, x bar, right? You're averaging a bunch of zeros and ones. So x bar is going to be the proportion of patients that died from COVID or died from advanced cancer or whatever. Minus pi 0, which is what we're hypothesizing, divided by the square root of x bar times 1 minus x bar. Again, x bar here is just a proportion divided by n. And this thing here goes to a normal 0, 1. So here, right, x bar, which is just this sample average, it's just the proportion of times that xi equals 1. Large values in magnitude, so values of z, absolute value, that are big, so, large negative values or large positive values are evidence against the null being true. Small values in magnitude are evidence of the null being true. So as an example, maybe we're going to flip a bunch of coins and we want to know if a coin is more likely to flip heads than tails. So I might test the null that pi, which is our coin flip probability of getting a heads, is less than 0.5 versus pi being greater than 0.5. Let's say I flip 20 coins, so n equals 20, and I get 18 heads, which means my sample average is 18 over 20, which is 0.9. X bar is 0.9. Then I plug in my test statistic here. So I plug it in, 0.9 minus 0.5. That's what I'm hypothesizing. It's fair coin is what I'm hypothesizing. Divided by the square root of 0.9 times 1 minus 0.9 over 20. All that together, I get 5.96. And you can see that here. I just calculated this here. Now what I'm doing here is just like we did for the t-test. This is what the test statistic should look like, be distributed if the null is true. Values in the middle of this bell-shaped curve are consistent with the null. Values outside of it are inconsistent. You can see out here, it's way outside of this bell range. So it's major evidence against the null. And if I want to compute this probability, sorry, I could compute the area under this curve to the right. Now, you don't have to use that formula. All you need to use is prop.test. So prop.test, the way that you're going to use it is you're going to plug in x, which is going to be your number of successes here, and n is going to be your number of total tests. So success, in the case of somebody dying, it's not really a success, right? But x here is the number of deaths in that case. And n here would be the total number of patients. P here is what you're going to test. That's your mu in the t-test. And you can do a two-sided alternative. You can do a one-sided alternative, either a less than or a greater than, all through this function. So this is the only function you have to know how to use. You don't have to use this formula. You just have to use this function. So here's an example. I'm going to do the same thing, right? I'm going to test whether pi is less than 0.5 versus pi is bigger than 0.5. So I'm going to plug in 18 here because I had 18 successes, 18 heads out of 20, 20 trials, p equals 0.5, and my alternative is greater. So all that's one line of code, and that does it. So here we go. I've got 18 out of 20. My null probability is 0.5. I get a large test statistic, and I get a small p-value. So this p-value is almost 0. It's less than 0.001. It's less than 0.05. So it's a significant difference. So since it's a small p-value, I can assume that I can conclude here that the null is false and that most likely the coin is biased in favor of more heads. I also get a confidence interval here, 0.77 to 1. Now in this case, right, before we saw our confidence intervals, one-sided had a upper bound of infinity. Here it's 1 because a probability can only be between 0 and 1. I can do the same thing with the two-sided test by using alternative equals two-sided. Here again, I get a very small p-value. You can see that here. So I reject the null that pi equals 0.5. So I reject the null that the coin is fair. And I get a confidence interval here. My confidence interval is 0.66 to 0.98. That's a 95% two-sided confidence interval. So what does that mean here? That means that I can say, hey, based on my data, it looks like the true probability of the heads is between 66% and 98%. So my 95% confidence interval is 0.66 and 0.98. Okay, another thing you might want to do is multi-category hypothesis test. So imagine the example, right? We've got advanced cancer, stages 1, 2, 3, 4, 5. Maybe you want to know, given that somebody has cancer, is it equally likely that they're in each cancer type? So here's another example. Maybe it's a variable xi that takes C category variable. So in advanced stages 1, 2, 3, 4, C is 4. If we have a Likert scale, C is 5. And I want to test this kind of hypothesis. I want to test collectively, is the probability of being stage 1 versus stage 2 versus stage 3 versus stage 4, all 1/4. So equally likely. But I can change that to be whatever I want. Maybe I'm assuming the probability of having stage 1 is 50%. Maybe stage 2 is 25%, and stage 3 and 4 are 10 and 5%, 10 and 15% respectively. I could test that. So how do I do that? I need to supply a vector of probabilities for each category. And I need to have that the probabilities all add to 1. So as an example, right, let's say I've got a dice roll. I've got a dice roll, I roll the dice, and I want to test if the dice roll is fair. So the goal would be to roll n dice, and I want to test the null. Pi 1, which is the probability of getting a 1, is 1/6. Pi 2, which is the probability of getting a 2, is 1/6. Pi 3, which is the probability of getting 3, is 1/6. Same thing for the rest. The alternative hypothesis here is that one of these conditions doesn't hold, which would mean the dice is not fair. So I can estimate the probability of each dice, true dice probability, by just looking at the proportion of times I rolled a 1, 2, 3, 4, 5, and 6. And that's this here. So I'm saying, hey, look, pi c hat, this is 1 over n times the sum of the indicators for equaling this category value c. So I can observe number of categories that I saw category C over n. Hat means it's an estimate. How do I do this? I get the expected counts of each category if the null hypothesis is true. And all I do here is multiply n, which is my sample size, times my hypothesized values at each category. So if I'm doing the dice example, it's n over 6. If the null hypothesis is true, then this test statistic has a chi-square distribution with capital C minus 1 degrees of freedom. So it's OC, which is my observed in each category, minus EC, which is my expected number of times that I would roll each category squared, on over EC. This is called a chi-square goodness of fit test. So just an example, right? I want to know if the dice is fair. This is my hypothesis. And let's say I roll a dice 60 times and I see 20 ones, 10 twos, 10 threes, 0 fours, 0 fives, and 26. If the dice is fair, we expect to see about 10 of each dice roll. So before we even get into statistics, this is fishy to me, right? I got 0 fours and 0 fives. That's strange. And it seems like the dice is maybe not fair if you saw that. Well, I'm going to calculate my test statistic. So it'd be 1 over 10, because that's the 1 over 10, because that's the expected count in each cell, times 20 minus 10 squared, because this is the number of ones, 10 minus 10 squared, that's the number of twos, 10 minus 10 squared, that's the number of threes, 0 minus 10 squared, this is the number of fours, 0 minus 10 squared, 0 is the number of fives, and 20 minus 10 squared, that's the number of tens or sixes. And I get a test statistic of 40. This is what the distribution looks like if the null is true. So just like in the normal distribution, it's a little bit different, right? Chi-square distribution is skewed. I think we talked about this in the first module. So test statistics that are way outside of this bell-shaped area are evidence that the null is not true. So here I reject the null, and I can conclude the dice is biased in some way. Now, how do we do this here? You don't need to use the formulas. You can totally forget about all that. That's fine. All you need to use is this function called chi-squared.test. So chi-squared.test, the way we're going to use it is you're going to plug in x, which is going to be your vector of counts, and you're going to plug in p, which is your vector of probabilities. That's all you need to do here. So we'll show you how to do that. X here, I'm defining a big vector x. X is equal to 20, 10, 10, 10, 0, 0, 20. That corresponds to the dice rolls that I saw. And P1 under the null is 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. Now I'm going to do a chi-squared test. I'm going to plug in my x value, which is this vector, and I'm going to plug in my p value, which is this here. I end up getting a very large p value, or a very large test statistic, and a very small p value. So this small p value is, so e to the negative 7 means it's 1.04 raised to the negative 7. It's a very, very, very tiny number. When you see negative 7, that means it's like 8 decimal places till you get to the first one. So this is less than 0.05. So we're going to reject the null that the dice is fair. Okay, so that's it for today's lecture. I just want to kind of jump into the homework and just kind of walk you through what I'm expecting for it. So we're going to go to our module 2 assignment. Here it is here. Okay, so what I want you to do is I want you to get the COVID data, the COVID pregnancy data from module 1, and I want you to answer the following questions. Test whether the proportion of term deliveries in this cohort is less than 80%. What test did you use? So hint, hint, it's something we covered today. What is a 95% two-sided confidence interval for this value? That's the proportion of term deliveries, the true proportion. Test whether the mean BMI is greater than 28. What test did you use? Test whether the median BMI is equal to 28. What test did you use? Both of these are from the first lecture. Okay. Next question. What is a two-sided 95% confidence interval for the population mean age in this cohort? What is a two-sided 95% confidence interval for the population median age in this cohort? Next, you're going to create a new variable for BMI groups. So BMI groups will be less than 30, 30 to 40 BMI or bigger than 30. All you need to use is use this code here. And then BMI group will contain this values. Now, this is a named variable. It contains 3 BMI categories. And I want you to test whether the 3 categories occur with equal probability. So that is related to what we just discussed. And then I'd also like you to create a 95% confidence interval for the mean BMI for patients that had COVID-19 and did not have COVID-19. And I'd like you to compare those confidence intervals. Are they drastically different? And that's the end of the assignment here. So just to point out, I really want to make sure and empower you all to do this. All you need to use, we actually didn't cover this yet, is 3 tests. You need to use this test, and this test. That's 3 functions. That's it. That's all you'll need to do to actually answer this homework assignment. And again, what I'm going to want is I'm going to want to see your computer output. You can use the snippet tool, which looks like this. I don't know if you've seen it. Snippet tool is really cool. You can copy it. I can come back in here and paste it. You know, I can put my code and then talk about it. Okay, this means blah, blah, blah. That's all I'm looking for you to do. So let me know if you have any questions. And this homework, I have the due date online, but we're going to keep up. It's going to be due, the end of the second week of class. All right, thank you, and hope you have a good week.